Okay, for today's construction, we will be building a Tesla single wire lamp as depicted in this picture. It is a very simplistic lamp. We just have the basic pear-shaped envelope, as is the case with modern incandescent lamps. We have the refractory filament. In this case, we'll use maybe 22 gauge tungsten. And then the support stem, which is just fused glass. The electrode connection, in this case, we'll use a nickel wire connection made into this loop here, and then secure the evacuation stem and evacuate the lamp as proper. Now, probably in a future video, I will be constructing his later developed design lamp, which is a spherical envelope, and then I will likely employ my improvements to the lamp in which the evacuation stem, instead of located on the top, is relocated elsewhere in the lamp so that to not allow stray discharges coming from the tip, which is a common issue with these type of lamps and early lamps from this era. So now we will begin the construction. Okay, we'll start by pulling a point. Let's turn our gas on. First anneal it a bit. We're working with 26mm borosilicate glass. It's of advantage, especially with heat application. Turn on our oxygen supply. Okay, we want to get it nice and hot, so let's see. We're going to take it off. Okay. Let's refine the tip a bit. And it doesn't matter if we have a very tiny tip on the glass, because that'll all be smoothed out with the application of the flame. Just take a bit off, just a tiny bit more. And let's even this out so that we don't have some off-centered hole. There we go. Okay, now let's even this out. Perfect. Okay. And we want to get it to a consistency like peanut butter, but not too soft, where it starts to cave in on itself. So we'll get it to that point, and then we'll blow through the hose just a bit to expand it. Not too much, we don't want the wall to be too thin. Reduce our oxygen. Okay. And we'll start blowing the sphere. Okay, we're getting to the point of which we have the sphere size that we want to work with. That's going to be maybe about 2 inches and a half. Right now we're just evening it out. And any irregularities which are presented on the front of the tube or the bulb, that'll be later corrected by the addition of the evacuation stem. Okay, now we're about to make the sphere size that we wish. So it's about 2.5 inches right now, just going based off the size of it. And a little more heat. Okay, we have the sphere that we want. Now we're going to extend the envelope downwards to create the pear shape. And this is done simply by heating the bottom half of the sphere and then blowing slightly into the tube to expand the glass wall, as you'll see right now. See, we've got to heat it up for a decent time because this is thick wall glass. So it should be about right there. Okay. And just a little bit more. We want to keep constant pressure behind the glass so that we don't necessarily get a warble. And if so, that's easily correctable. So let's just expand it just a tiny bit more. See, we're getting a bit of a warble. Okay, we have our pear shape. Now next step is to add the evacuation stem that'll go here on the front. So for that we'll need to change torch tips. Okay, now we've exchanged our torch tips for a finer point. Now I will heat up this part of the glass so slightly. Front part. And we will then blow into it. Okay. Now we're going to blow hard and essentially pop a hole through this glass here. There we go. And we want to give ourselves a little room here so that when we add the evacuation stem, it's able to form a lip or a cusp on this opening. So we want to leave maybe about that much. Okay, and let's anneal that just a little. Like I said, it's borosilicate glass, or what's known as Pyrex, but even still, because we're dealing with irregular wall thicknesses, it's a good idea to anneal, otherwise the whole thing will just crack and shatter. Okay. Next step is to cut the glass and remove the bulb from this tubing. So that will simply use a glass cutter. Okay, now we just cut the envelope. Here is the lamp. Nice clean cut. And now we'll start the process of washing it so that to remove the fine particulates and other glass particles inside of it so that it doesn't interfere with the vacuum process. And then we'll attach the evacuation stem. Okay, now to make the evacuation stem, here we have some 6mm glass. Now it looks a bit off because I've joined different pieces of glass, but the interesting thing is that because of the vacuum pump and the vacuum seal, it requires a very specific diameter glass tubing to sit into the socket. So, of course, with a millimeter of difference, it won't be able to fit. Thus, I have secured the correct diameter tubing here, and this will essentially be the flared piece that connects to the bulb. Now, the thing to remember here is that only this section or this amount of the glass is going to adhere to the bulb and will be sealed off probably from this point. So this is just all going to be scrap, and that's why it doesn't exactly matter how it looks. It's just how it performs in this case. So what I'm going to do is place it in the flame and flare it. Give it a little cusp so that it adheres to the cusp or mound formed on the top of the lamp. Heat it up just a bit because it is thin glass. It heats up faster. And we'll place our tool here, turn it, and then slowly start to flare it. Okay, we're getting a flare. And the idea here is to continuously turn it, otherwise you'll get a very undesirable shape. Okay, let's see, maybe just a little bit more. Of course, the size of this cusp or this flare has to correspond to what was formed when we popped a hole through the top of the glass of the bulb. Okay, that seems about right. Okay, turn the oxygen off, anneal it, and then the next step is to get our lamp or envelope, and then we're going to simply seal it to the top here. Now let's just anneal this a bit because it is slightly thinner here at the tip, so that we do have a considerable irregularity or difference of wall thickness, and just applying the heat directly to it will crack, and I've lost many bulbs like that in the past. So we just want to be on the safe side here and not waste any material or time. Okay, a little more. And this bulb, I just washed it with scalding hot water so that to remove any particulates, like I've said before. A little more. We want to build a nice sooty layer on the glass, and that's easily wiped off or just burned away with the oxygen. Anneal this a little more. Okay, and let's turn the oxygen back on. We want it on low flame. Since this is thinner glass, we don't want to melt it completely. Okay, there we go. Okay, now we're going to want to heat this part up just a little. And start to adhere it. Okay, made our connection. This is the careful part. We have to make sure it's all even. Okay, so far so good. There's a little hole right there, but that's easy to fix. Okay, good. More. Okay. Okay, and then we want to slowly turn the lamp, the envelope, so that to even out this part of the evacuation stem. Like I said, this requires very careful hands. A little more. And we want to be sure as to not stretch the glass and the evacuation stem, otherwise we'll form a really tight pinch of uneven thickness, and that'll just result in disaster when we're sealing it off the pump. Okay. Almost. Okay, that'll work. Let's give it a quick test. Okay, I don't think there should be any leaks. We always do a soap test, spray any part or any joint where glass meets glass with some soapy water and blow through that juncture to see if there's any bubbles formed by the passage of air indicating a leak. And that's always repairable to some extent. Okay, that looks good. Let's see, let's correct that bend just a little. It doesn't matter if it's completely straight or at a slight angle because it'll be sealed off after. So there's really nothing to fret about right there. Just a little more. Okay, there we go. Now let's anneal it. As I've stated before, if we fail to anneal, especially something such as this, which is relatively thin, or this part of the lamp process, then we will get a cracking around the top of the envelope, either if we apply the slightest of heat afterwards after we let it cool down, because I must note that in the lab right now it's about 40 degrees Fahrenheit, so of course that temperature difference after the glass is worked with heat, that significantly could cause damage in the form of cracking, so we want to anneal this quite well. Okay, that should suffice. And we have the stem now sealed to the envelope. I bring it close to the camera. It's covered in soot right now, but once that's removed, then we'll have a nice lamp. And like I said, it'll be sealed off the pump at around this juncture. So the rest of this glass is simply going to be scrap or used for another bulb on the evacuation process. And then we'll have our electrode that sits in here, and it'll sit upside down like this on the pump and eventually sealed off. So let's proceed to the next step in making our electrode, which is the fun part. And now we're going to secure the electrode. So for the electrode material, we'll be using 22 gauge tungsten wire. And for the actual electrode base connection, we have 20 gauge nickel wire, which is suitable to make the end tip for the lamp. And to adhere that to the tungsten or the lead-in filament, we'll be using some nickel sheet, which will bend into a tiny little tube because nickel tubing is quite scarce to come by. So in order to do that, I'll take some pliers and I'll simply bend the sheet and form a small tube, like so. And there's a tiny little tube which is basically the curled sheet, and I will then clip it off. There we go, we have a small tube, and let's bend it a little more. Okay, now we have a very tiny tube. Next, we will take the nickel and create our connecting base, which is simply a small loop. This kind of loop design was quite common for these early tubes, not only Tesla's, but I mean other various vacuum tubes, including the Crookes tube and certain early incandescent lamps. So all it is, I mean, it's just a metallic loop structure that connects to the filament. Let's see, we're almost done. Okay, there we go. Let's flip this off. Nothing that intricate or complicated here for the connecting base. Here, I'll bring it up to the camera. Simply a tiny loop, which is designed to connect, or I guess string, to any wire, almost like a tiny pendant lamp. Yeah, we will cut it a little more to length, maybe about right there. Okay, and now we will connect the tube at the halfway point and secure it to the nickel. So all we have to do is just squish it down with the pliers. There we go. And I will further squish it down some more. There we go. And that creates a decent connection. Now we'll take the lamp for size reference, and this is essentially the lead-in stem glass seal part, and this will go inside the lamp, and we'll use the lamp to determine the relative size which the filament and wire has to be. It should be around that size. So that's about 3 inches in length, give or take. Let's cut it. And let's just straighten it out a bit. Okay. Now we have a nice straight piece of tungsten. Almost straight. There we go. Okay. And this will adhere to the nickel. There we go. There we go. We have it nice and secured. And we'll simply do the finalized bending after we spot weld it. So to spot weld it, we have our spot welder on here. Let's turn it on. And we'll simply place it in between the 2 electrodes here. First we'll do the nickel section. Simply push on the press button. There we go. And it spot welds it. We'll do the next one, which is the tungsten side. Okay. And that forms a decent seal. We'll just do one more weld in the center to make sure that they're nice and tight. Okay, that's welds them. So now we essentially have our nickel and tungsten filament wire, which is this piece, connected, and this will essentially be pressed in the glass of the metal to seal base of the lamp, so that only this part of the nickel, which is the wired connection, will simply protrude through. So to give an idea of how that'll look, we have the base here, and then the lead through glass, which will essentially sit through the lamp as such. Now, one thing I want to point out is that this glass tubing is made a little bit longer because there is a slight retraction of the glass by about ½ a centimeter to 0.8 centimeters. So we have to compensate for that. Now, it does look a bit longer than what it should be according to the picture which Tesla put forth, but for this purpose we just have to make sure that it is the right length even after making the seal to the stem. So that'll be the next step. To secure the filament to the lead-in glass stem, what we're going to have to do to the filament wire beholding the nickel base electrode is we're going to have to heat up this tungsten wire in direct flame to a red hot, white hot temperature, because we want to build up an oxide layer on this tungsten wire so that when it adheres and seals to the glass stem, that it ensures a nice tight vacuum seal. Otherwise, we're going to have irregularities on a very microscopic level, and that's not going to be beneficial in any way. So I'm going to now heat up the tungsten. I do this slowly just by incremental variations of placing it in the flame and out of the flame. And I let it heat up to a red hot. And then I have the pliers on the nickel because nickel isn't exactly as heat resistant as tungsten, so by shielding it with the pliers I avoid subsequently melting it. So now let's heat it up directly. And get it to a white hot. And now a nice layer of oxide is on the surface of the tungsten. And it's okay just to heat up a tiny bit of the nickel so that to remove any stray oxygen molecules that may be sticking to the nickel surface. So this just pretty much removes a decent part of contaminants which would otherwise impair the vacuum. Let's heat it up some more. Okay, and then more pass. Okay, and there we go. So now we will take our glass stem and place it through to where we want it, roughly. So about right there. And now I will heat up just a little portion so that to give me grip. And then we'll start to melt the rest of the glass. So what's happening is that this glass tubing is very thin and small, so that by heating the glass, it'll simply stick to the tungsten. And this is a practice that was commonly used back in Tesla's days for high vacuum lamps. That you'll see most of the lead-in stems that there isn't much of a gap between the lead-in electrode and the support stem because the glass is directly sealed to it. And this is a very smart practice which does and does not persist in this modern world. And that's pretty much it. There it is. We have the stem now sealed to the glass lead-in. And let's just anneal it a tiny bit. Doesn't really require that much, but nonetheless, to be on the safe side. And then the next step, which is the second to last final step of the glass blowing process, is to actually seal this inside the glass envelope. And we will do that shortly. Okay, before sealing the electrode into the envelope, we have to anneal this portion of the glass so that to avoid undue cracking. And we simply pass it through a yellow propane flame. And at this point I want to mention the setup I'm using. So I employ oxygen and propane as my heating source. Of course, one could also use oxygen and natural gas from the main supply for the house or suburban use. That'll work, but typically, that requires a more elaborate fixture, and propane is easily to acquire in tanks. So we are almost done annealing it. Although this part of the glass is fairly thick, I have had it in the past where it does crack, especially when the ambient temperature is cold. Okay, more. We want to build that nice sooty layer. Okay, now what we're going to do is we're going to inward flare this flange, or this opening, so that there's a tighter opening for the electrode to sit through. And then we'll blow through the evacuation stem once the electrode is fixed into position, so that to round out the bottom a little more. Okay, that's good. Now let's turn on our oxygen supply, and we'll round it out. Okay, now even though the size of the hole in the bulb is a bit large, we could still manage with that simply by inserting the filament structure in, and by placing it in, we could then start to move it around and start to slowly close the hole simply by stretching it. Okay, we have just finished the seal of the filament. We have the soot covered at the base of the bulb during the process of annealing, which now we will simply take off with a rag and some water. So for a closer inspection, this is the bulb as it is now. We can see that the base has the connection like so. Now by simply being very careful so that to not extenuate the pressure on the bulb, simply wipe it off. And it's best to wipe it off now prior to the bake-out process and prior to evacuation, because typically from what I've noticed that the bake-out process will cause the soot to bake in quite intensely into the glass, and it becomes a little more difficult to actually take off that soot without some type of abrasive application, which could otherwise damage the bulb. Okay, let's take a little bit of soap, some soapy water, please spray it into the rag and apply it alongside the bulb. And this ensures a nice clean glass surface, which is more presentable, but also gets rid of any conducting surfaces such as the carbon, even though carbon is a semiconductor, from the soot, that is, that could alter the operation of the bulb and usually direct undue heat to the bulb where it's not supposed to go. Okay, it's almost done. Quite a bit of soot is being removed. Okay. Now for the clean side of the rag to polish it and get rid of the soap and remnants of it. Okay, let's see, I think we have a layer here of some built-up soot. Oh no, that's simply water moisture. Okay. So, the fogging of the inside of the glass, which could be slightly seen if the camera is able to pick it up, that's not permanent. That's simply the expulsion of water moisture from within inside the wall of the tube. And that'll be definitely removed during the bake-out process and just the overall evacuation step. So next step is to place this on the pump. Now we're at the evacuation stage. We're sitting on top of the pump assembly. Here's the opening. Okay, for the tube and the evacuation stem, I have here a clamp nut with a small O-ring and flange on the inside. And what I'm going to do is I'm going to place that on there, place an O-ring of roughly the same size, and apply a small amount of vacuum grease to this O-ring. and just apply it to the entire O-ring and slight amount of the glass that's around it. Okay, this ensures a nice tight vacuum seal. Then I'll place the fitting over it. And what this is going to do as I sit it into the receptacle and clamp it down is it's going to squish this O-ring tightly around the glass, which ensures a very high vacuum seal and does not permit any gases to escape or enter. So I will now secure it, and it sits in there. Now I will tighten it more so. Not too tight, otherwise the O-ring, which is being clamped down around the glass tubing, will actually cause the glass to shatter and break off. So we want to be fairly gentle and obtain a feel for it. So around there, that's perfect. Okay, now I will turn the pump on. You will hear it come to life. And we can notice that as the pump was turned on, most of the water vapor that was on the inner wall of the glass suddenly ceased to exist. It was sucked out. So now I will turn the lights off and test the vacuum with a small flyback transformer. And we can see that purplish hue, which indicates the presence of nitrogen. But we also see a bluish white occurring near the bottom of the evacuation stem. That is the oxygen trapped inside the bulb. Now we'll notice that this purple will start to go away and start to manifest a bluish whitish color, which means that a higher vacuum level is being achieved. And because of this, the rapidity of this color and its quick change, we could determine that there are no leaks inside this bulb, which is a good sign that the process was a positive one. And what we'll do is have this pumped down for maybe about 5 minutes without the bake-out oven on it just yet. And what we're going to do is hook up the diathermy machine to the lamp and physically drive out all the contaminants and water molecules found within the filament, as well as the inner wall of the glass. So by using these high frequency currents, we will be able to evacuate the lamp even further, as the bake-out oven cannot necessarily release all the contaminants found within the filament. The lamp has been sitting on the pump now for about 10 minutes. We've extended the 5-minute period to now 10. So that, because it's a larger vessel, it requires a little more time for it to pump down to a moderate degree for us to perform the high frequency tests. Now what's being seen right here is a wire which connects directly to the output of the diathermy machine. No extra coil is used in this case, as we do not require those excessive potentials just yet. We are simply connected to the cauterizing pin of the diathermy machine. So I will turn the lights off now and initiate the machine at low power. And we see that the bulb is now giving off a rather beautiful whitish hue, which indicates the signs of oxygen that's being thrown off from the filament. Now I will shut the device off and let the bulb degas. Now turning on the diathermy machine again, let's see what occurs. And what's interesting, that I just turned it off, but as the diathermy machine was operating, we saw the bulb become dark, and it seems to have exhausted itself, indicating that the vacuum is actually higher, now well above the striking vacuum of where plasma starts to formulate, meaning this bulb is now in a suitable position for higher power treatment through radio frequency, but also for the bake-out oven process. Now I will increase the power to a higher level, and we could see, there we go, that the filament just started to reach some incandescence as more projected matter in the form of water vapor was just thrown out. So let's try the power again. Okay. Now our filament is reaching incandescence. That's good. Okay, perfect. Now we have to monitor that the vacuum grease and other sealants don't heat up with the RF, which it does have a tendency to do, so that's why we have to keep these tests fairly brief but continuous. Let's see on low power again. Bulb doesn't light up, but if I bring my hand near it, still doesn't light up. Okay, that's good. We are achieving high vacuum. Okay, now by adjusting the spark gap, we're able to increase the potential, and the bulb illuminates. And the filament now does not incandesce. So what will now be done is we'll let the bulb cool for another 5 minutes. We will ramp up the power to full power at once, then shut it off and do it again likewise. And this repetition will conceivably throw off more contaminants as the vacuum is now higher. So let's give it 5 more minutes. Okay, 5 minutes has elapsed. Let's ramp the power back up all the way now. Interesting. As you can see, the ozone generated on the lead wire going to the bulb, that is heavily illuminated, as well as the essence of ozone in the air. But the bulb remains dark but slightly flutters, which is indicating that there is a very high vacuum, at least respectively what is achieved by the roughing pump, that does not allow for the bulb to reach a level of phosphorescence that easily, even at full power. So let's try it once more. Okay, now I believe we have to adjust the spark gap to raise enough potential to excite the phosphorescence inside the bulb. Let's try that. There we go. And we reached incandescence for a brief moment. The filament's still glowing. Now it is diminished. Let's do it again. And we have full incandescence. A very bright display indeed. And you could notice that as the filament incandesces, that there is less phosphorescence of the plasma around it as the filament reaches a higher degree. And this is, hypothetically speaking, the ejection of water contaminants and what have you emanating off the filament at rapid velocities, therefore being sucked out and pulled mechanically by the vacuum pump. So that means this bulb is reaching a very high level of efficiency. Now let's ramp the power up for one more time, and we'll put the bake-out oven on it. Okay. Let's remove these terminals. Okay, and now we will place the bake-out oven on top of it. Okay, this is the oven. Simply has a coating of nichrome wire on the inside, which is supplied by mains voltage. If I situate it on top of the bulb, we use tape to secure the bake-out oven so that it doesn't move around from the vibrations of the vacuum pump. Okay, now it's centered. I will now turn the power to the bake-out oven, and I will bring it to 60 volts, halfway, as it is capable of taking the full 120 volts from the mains. But because it is a heating element, and because it is around a sensitive device such as a bulb, which is glass, we want to slowly bring up the temperature and not rush it so suddenly. Let's see. The chamber is warming up. Okay, and as the chamber warms up, we will start to slowly increase power going to it. We are at about now 3/4 of the way. And this simply ensures that the glass is able to conform to the addition of this temperature. Granted, it is not soda lime glass, which would otherwise crack violently by the application of heat to it. And the prior tests, I must note, which involved high frequency, that ensured the long lifespan and longevity. Okay, we have applied full power to the bake-out chamber. Now we will let this sit operating for exactly 3 hours, which allows for all the contaminants and unwanted matter inside the bulb to be fully evacuated. This will ensure decent longevity of the lamp, as well as its efficiency. Well, it's been approximately 3 hours since we placed the bake-out chamber on the bulb. Now it's about time to shut it off and seal the tube off. So I've went ahead and turned the power off to the chamber, and it has now cooled to ambient temperature. So I will remove it carefully without disturbing the bulb. And now the bulb is essentially ready to be evacuated from its stem. Now the first step from evacuating it and liberating it from the vacuum pump is essentially to add heat to the system. I will employ a yellowing flame, a propane flame, just to free any extra contaminants in the bulb. This is usually done as a finalizing step, just to carefully move it around the lamp. And once we're done with this, we'll let the bulb just sit for maybe 5-6 minutes, just to let anything that was trapped get pumped out. And then we'll be able to evacuate it from the stem and seal it at the base. So let's just let this cool after. Also, the process of doing this allows the bulb to anneal even further right before we apply the flame, so that we don't necessarily shock it and then result in a crack. This is just also another precautionary step which is taken. Okay, let's let that sit for a couple minutes. Okay, now we will start the sealing process. I will turn on the flame. And I will adjust it. This is the tricky step. This is either what makes or breaks the bulb. Either we succeed in taking it off the pump or we don't. Let's hope that this is good. Okay. Now I will start to heat up the glass around the stem. What it's going to do is I heat it up, it's going to want to start to close in on itself. And that's what we have to watch out and take advantage of as well. Okay, it's wanting to close up. Now let's seal it off. Okay, success. We have sealed the lamp off. It's covered in soot, but just like before, we'll just take the soot off and it'll be done.